This lecture is going to be all about applications of the Sylow theorems. And the first application we're going to give is to classifying groups of order 12. So we'll show that if G is a group of order 12, then G has a normal Sylow 2 subgroup, or it has a normal Sylow 3 subgroup. Of course, it could have both. I mean, that's what happens, for example, when G is an abelian group of order 12. So in order to prove this theorem, we're going to start by proving a lemma about counting the number of elements of order p in a group. So let's say that p is a prime. And if G has k subgroups of order p, then G has k times p minus 1 elements of order p. And the idea is just going to be first to note that every x in G with order p is contained in some subgroup of order p. I mean, which one? It's definitely contained in the cyclic subgroup that it generates. So we can find all of the elements of order p by just adding up all of the elements of order p in all of the subgroups of order p. So inside each subgroup of order p, how many elements of order p does it have? Well, every non-identity element has order p. So there are p minus 1 elements of order p for each one of these k subgroups. So we just need to make sure that if we go over all of these k subgroups and add up the total number of elements of order p in each one, we need to make sure that we didn't double count some things. Like, what if there's some element of order p that's in exactly 2 of the subgroups of order p? Well, let's see that that doesn't happen. So if h and k are distinct subgroups of order p, we claim that they intersect trivially. So what would that mean? If you have p minus 1 elements of order p in h and p minus 1 elements of order p in k, how many elements of order p are there in h and k together? Well, every non-identity element in h does not appear in k. Every non-identity element in k does not appear in h. So you would get p minus 1 here, p minus 1 here, 2 times p minus 1 total. So that's the idea. So how do we know that the intersection is trivial? So by Lagrange, h intersects k is a subgroup of h. So the order of h intersects k divides the order of h, but that's p. So what does that mean? The order of h intersects k is either 1 or p. But we know that h intersects k is less than p because these are distinct subgroups of order p. So that means that there's something in h that's not in k. There's something in k that's not in h. OK, so what does that say? So there are k subgroups together, k subgroups total of order p. There's p minus 1 elements of order p in each one. There's trivial intersection between each pair. So we just go through our k subgroups and add up p minus 1 elements of order p in each. So I'm going to pause and erase, and then I'll show you how to use this lemma to prove this statement about groups of order 12. Now let's prove this theorem about groups of order 12. So we want to show that if G is a group of order 12, then G has a normal Sylow 2 subgroup or a normal Sylow 3 subgroup. We know that that's the same thing as showing that the number of Sylow 2 subgroups is 1 or the number of Sylow 3 subgroups is 1. So let's use Sylow 3, the third part of the Sylow theorem, to see what are the possibilities for n2 and n3. OK, so n2 is 1 mod 2, and n2 divides 3. So that means n2 equals 1 or n2 equals 3. Both of those seem possible. n3 is congruent to 1 mod 3, and n3 divides 4. So n3 equals 1 or n3 equals 4. Both of those seem possible. So what we want to show is that at least one of these needs to be 1, that there's a normal Sylow 2 subgroup or a normal Sylow 3 subgroup. So let's suppose that n3 is not equal to 1, because if n3 equals 1, there's a normal Sylow 3 subgroup, and we're done. So if n3 is not 1, then it has to be 4. So now, by this lemma that we just proved, we have these 4 different Sylow 3 subgroups. Each one is isomorphic to z mod 3z, right? It has order 3. So how many elements of order 3 are in those 4 subgroups? Well, it's 4 times 3 minus 1, the number of non-identity elements in each. So this group G contains 8 elements of order 3. All right, so clearly a Sylow 2 subgroup doesn't have any of those elements of order 3 in it, right? Because the order of a Sylow 2 subgroup is a power of 2. So how many elements are in a Sylow 2 subgroup? 4, because 4 is the highest power of 2 dividing 12. 8 of these 12 elements have order 3. So there's only 12 minus 8. There's 4 elements unaccounted for. A Sylow 2 subgroup has size 4. So these 4 leftover elements are the only things that can go into a Sylow 2 subgroup. So these 4 elements together are a Sylow 2 subgroup. But that means there's exactly one, because if these 4 leftover elements all go into the same Sylow 2 subgroup, what other elements could go into a different Sylow 2 subgroup? There's just nothing left over. So because there's a unique Sylow 2 subgroup, that's it. So if it's a unique Sylow 2 subgroup, that means that it's normal. So what we've shown is that if n3 is not equal to 1, then n2 is equal to 1. Okay, so the next thing we're going to do is prove something stronger, to say that if G is a group of order 12, then either n3 equals 1, that you have a normal Sylow 3 subgroup, or if n3 is not equal to 1, G is isomorphic to A4. And we've done a lot of work already to say that if n3 is not 1, n3 is equal to 4, and it has these, G must have these 8 elements of order 3 together, and there's this normal Sylow 2 subgroup. So I'll pause and erase, and then we'll see how that gets us to A4. Let's prove this stronger result about groups of order 12. We want to show that either G contains a normal Sylow 3 subgroup, or if it doesn't, then not only does G contain a normal Sylow 2 subgroup, but G must be isomorphic to A4. Okay, so we saw before that for a group of order 12, either n3 had to be equal to 1 or n3 had to be equal to 4. So if n3 is not equal to 1, that means there's 4 Sylow 3 subgroups. Each one has size 3. And that means in these 4 subgroups, each one has 2 non-identity elements, so 2 elements of order 3, and they intersect trivially, each pair of these 4 Sylow 3 subgroups. So we get 8 elements of order 3 in G. Now, how are we going to show that G is isomorphic to A4? Well, if we can get G to act on a set of 4 things, that'll be a start, because that'll get us a homomorphism from G to the symmetric group on those 4 things. Here's our group action. G acts on this set of 4 Sylow 3 subgroups by conjugation. So this gives a homomorphism from G to the set symmetric group on these 4 Sylow 3 subgroups. And this is isomorphic to S4, because any symmetric group on 4 things is isomorphic to S4. So the idea is going to be to prove that G is isomorphic to A4 by using this homomorphism. So our first claim is that the kernel of phi is just the identity, that this map is injective. So let's write down what it means to be in the kernel. That is the set of all elements in G, so that this action by conjugation just fixes every one of the Sylow 3 subgroups. So it's the set of all G in G, so that G, Q, G inverse equals Q for all 4 of these Sylow 3 subgroups. So let's zoom in on one of these Sylow 3 subgroups, Q. Well, if G fixes Q, that means that the element G is in the normalizer of Q. So the kernel of phi, whatever it is a subgroup of the normalizer of Q. How big is the normalizer of Q? Well, by Sylow 3 star, n3, which we know is equal to 4, is equal to the index of the normalizer of Q in G. So you just pick any one of your Sylow p subgroups, and np is equal to the index of the normalizer of that subgroup inside G. And what does that mean? So G has order 12. So if this index is 4, the normalizer better have size 3. Well, clearly Q is contained in its own normalizer, but Q already has size 3. So that means that Q is actually equal to the whole normalizer. So what have we seen? We've seen that the kernel of phi is a subgroup of the normalizer of Q for each one of these Sylow 3 subgroups Q. But each one of these normalizers is just a subgroup itself. So the kernel of phi is the intersection of all 4 of these Sylow 3 subgroups. But any 2 of them intersect in just the trivial element. These are 4 groups of order 3, so they have to intersect trivially by Lagrange's theorem. What does the first isomorphism theorem tell us? It tells us that G mod the kernel of this map is isomorphic to the image of this map. But we've seen that the kernel is the trivial subgroup. So G mod the trivial subgroup, well, that's just G, is isomorphic to the image of this map, which is some subgroup of S4. Which subgroup is it? Well, it has to have size 12. And moreover, we know that G contains 8 elements of order 3. So that means this subgroup of S4, the image of phi, also contains 8 elements of order 3. What are the elements of order 3 in S4? They're exactly the 3 cycles. Why is that? Well, how do you compute the order of an element in Sn? You write it as a product of disjoint cycles, and then you take the least common multiple of the cycle lengths. This is something that we saw on the first homework. So what does that mean? The image of phi is a subgroup of S4, and it contains 8 3 cycles. But all those 3 cycles are in A4. So the image of phi is a subgroup of S4, and A4 is a subgroup of S4. The intersection of the image of phi and A4 is also a subgroup of S4, but more importantly, it's a subgroup of A4. What size does this subgroup have? Well, it's at least 8. But the order of a subgroup of A4 has to divide 12. So if you have a subgroup of A4 of size at least 8, then it's actually all of A4. So what are we seeing? We're seeing that the image of phi contains so many 3 cycles that the image of phi must actually be equal to A4, and that is the end of the proof. So we haven't quite classified all groups of order 12 up to isomorphism, but we're close, and this is something that we'll be able to do within a few more lectures.